Hi everyone, I am Kshitija Kelkar and I am a postdoc at University of Valparaiso in Chile. And today my poster talks about a recent work in understanding the evolution of star formation in a unique nearby emerging cluster, Abel 3376, which underwent a major merger 0.6 gigayears ago and which produced some large-scale post-merger shocks observed as radio relics. So just to summarize, our work establishes for the first time in the same system twofold environmental effects that affect the star formation in galaxy, which lead to quenching as well as continued star formation, right from the pre-merger state to the post-merger state. We also put forward the possibility that the merger shock might be affecting low and high mass might be affecting the star formation in low and high mass spiral galaxies. So if you want to know more about this exciting result, please look at my poster at B12 in GatherTown.
Hello everyone, I'm Avinash Chaturvedi, a PhD student at ESO in Gashing. My PhD deals in understanding the mass assembly of the Fornax Galaxy Cluster. So how does a galaxy cluster assemble and grows is a long-standing question. And we are trying to answer this by performing the dynamical mass modeling of the Fornax Galaxy Cluster using global clusters as the kinematical tracer. Here in my poster A12, I'm presenting one of the most extensive radial velocity catalog of global clusters belonging to the Fornax Galaxy Cluster. Here in this plot, I am showing the radial velocity map of the full sample of global clusters overplotted on the photometric surface density map of the global clusters, shown in the white color. My work provides strong kinematical support to these substructures of the Fornax cluster. To know more about the system, please check poster 812 on the GatherTown. Thank you.
Hi, it's still not well understood what is the impact of cluster mergers and group accretion on the evolution of galaxies, and in particular on gas stripping and the formation of jellyfish galaxies. There are no homogeneous studies made on big samples making the proper corrections, for example, considering the same physical radius for the counting of the jellyfish signal clusters. So we classified the dynamical stages of the wing surveys using many different proxies to have a robust classification of this very homogeneous sample. Then we counted the fractions of galaxies undergoing run pressure inside R200 with respect to the number of blue spirals in the same aperture. We found no evidence of run pressure enhancement in disturbed clusters. This was a very careful analysis that will be useful for many kinds of galaxy evolution studies, since here we are minding about possible bias, such as aperture, completeness, coverage, and corrections with respect to the infalling population.
Yes, I am César Caretta. Good morning from Mexico. Well, the poster is about a study of the evolution of nucleation zones in superclusters of galaxies. What are nucleation zones? They are the regions that we expect to be the future largest galaxy clusters. In some sense, the nucleation zones are for these giant future clusters, what the proto-clusters are for the massive clusters that we have now. Well, for finding these structures, we search for the densest regions that are gravitationally bound. Here are, you can see two examples in the Coma-Leo supercluster. It has two cores, one in Coma cluster and the other in Abel 1367. More details in the poster A9.
My work mainly centers around two galaxy clusters at redshift 1.4, so-called cosmic noon. We're interested in quantifying and analyzing any quenching mechanisms that may be going on in galaxies in these clusters. In order to do that, we've got Amos IFU data for about 25 of the galaxies across the two clusters, along with complementary photometry. Combining these two data sets really lets us do an expansive look at the analytics of these galaxies, kinematics, some morphology, star formation rates, the mass content, gas depletion time, examples shown on this slide, it will really let us get into what could be causing these quenching events or the quenching mechanisms. For more information, please see my poster. It's A2.
I'm here. Hi, everybody. Yeah, let me talk you very briefly about our Amos survey on star-forming galaxies in two redshift 1.5 proto-clusters. We find a high fraction of disturbed or very compact gas disks. However, the regular rotators in the sample, there we don't see a difference between the proto-cluster Tully-Fisher and the field Tully-Fisher. And the disturbances that we observe probably are driven by gravitational interactions and less likely by hydrodynamical interactions, because the relative velocities of these proto-cluster members are rather low. They feature a velocity dispersion of just 300 to 400 kilometers per second. So if you want to know more, contact me or look at the poster or both. Thank you.
Yes, hi everybody. I'm just presenting our survey, which is GCAV, which is a second generation Vircam, ISO Vircam public survey, which is I aim to observe 20 massive galaxy clusters. You can see the list of the clusters here in the table. And for the technical details, you can go to the website. And in green, you can see here those clusters for which the observation in J8, Y, and KS band has been completed. And we release the data to ISO, and which means that the infrared data are public available worldwide. And for most of these clusters, also a lot of ancillary data, as you can see on the right, are also available. And so have fun to explore the data set.
Hello, everybody. My name is Anastasio Díaz-Sánchez from the Universidad Politécnica de Cartagena in Spain. In this poster, I present an algorithm to find high-energy galaxy clusters, proto-clusters, and filament. This algorithm uses asymmetrical convolution plus friend-to-friend algorithm in order to set asymmetrical overdensity. We have found 100 of these galaxy cluster redshift 1 using WISE, and also made color cut in this time as well. We have followed up 10 of them with GTC EMIR and 2 with multi-object spectroscopy. Okay, thank you very much. You are interested. We are in the A16 number. Thank you.
Okay, hi everyone, I'm Lýdia Štofanová. I'm a third year PhD student at the Leiden Observatory in Estron, and I will be showing you the results of my upcoming paper that deals with the ionization by galaxy cluster photons that actually alters the ionization state of the nearby warm hot intergalactic medium. And as we all know, the photonization, it is common to assume that the photonization is caused by the cosmic UV or X-ray background, where in our paper we actually show that also galaxy cluster photons can act as an additional source of a photonization. And one of our main results can be actually seen on the right-hand side plot, where we see the ion fractions here in this case for 0.7 for a specific temperature. And based on the densities and on the distances from the galaxy cluster, we can see that instead of getting for a specific density one number that would be assumed if you, let's say, assume this collisionally ionized equilibrium, or actually the photonization source is just the background, we actually get the whole range of ionization or of ion fractions. And if you are interested in more details, let me know via email or contact me on Slack.
Hi, I'm Guillaume. I'm a postdoc at the University of Durham. I would like to thank the organizer to giving me the opportunity to present you my work. The motivation of my work is at the top left panel, where you can see a mass redshift distribution of some of the SPT clusters, with the 2 line being the mass growth of clusters. And in this diagram, I modeled with strong gravitational lensing 2 clusters and found in one a 1% sub-Elo mass fraction, and the other one 33% Elo mass fraction. And to go further investigate what there is such discrepancy, I used the velocity dispersion mass relation illustrated on the top right, and on the data illustrated on the bottom left panel, which is the A370 Muse coverage. And you could see on my results on the lower right panel, which are the derivative mass from the dynamical fits against the strong lensing mass with the cluster. And you could see that does not follow the one-to-one line. There is a slight tilt. And if you want to chat about that, let's see my poster at C3.
Oh, hello, everyone. This is Guillaume from Tokyo University in Japan. And here I'm introducing this poster about galaxy quenching dependence on stellar mass and environment. So in this work, we are using multiband photometric data and apply rest frame UVJ diagram to classify quiescent galaxy, recently quenched galaxy, and star-forming galaxy. This method, we confirm it with some dynamo spectra. Also, we use some model evolutionary tracks with different quenching timescale to separate fast and slow quenching galaxy. The number ratio of slow over fast quenching galaxy, the quenching efficiency, and quenching stage are the three main parameters we use to quantify the quenching process. We found that mass quenching is mainly affecting high mass galaxy. The environmental quenching is mainly affecting low mass galaxy. The quenching timescale and quenching stage are both depending on the stellar mass. We also discussed some possible quenching mechanism of two specific cases. If you are interested in this work, please come to C4 to check my poster for more details. Thank you very much.
Yeah, hello everyone. I am Satoya Nakano, a first-year graduate student at Nagoya University in Japan. I am going to show you a strip gas that was first detected at Z-1. This time we observed SPT 0615, a massive cluster at Z-1 using ALMA. As a result, 4 galaxies are detected by dust continuum from one field of view of band 7, and 3 galaxies are also detected by CO524. In addition, SMG1, the brightest galaxy among the detected galaxies, shows tail structure. This tail structure may indicate ram pressure stripping because the SMG1 HST image looks like a jellyfish galaxy. This is the first detection of gas stripping at Z-1. There is also evidence of stripping by SMG1. If you'd like more discussion or information, please talk to me on Slack. Thank you.